Right. Hey guys. So today we'll be presenting about our synthesis and analysis of 4-chlorophenyl hippurate. And yeah, I'll let you take it away.
Yeah. Okay, so first part, we have the overview of the experiment. So initially what we did, we synthesized hippuric acid through glycine and benzoyl chloride. So the main purpose of the experiment, however, was to successfully synthesize 4 phenyl hippurate. Yeah, that was a general purpose. And then so in the second step, what we did was we did an ester preparation through a reaction of alcohol with hippuric acid. And this is dehydrated using EDC. For the third day, what we did was we did a UV profile of the starting material and the hydrolysis mixture. We monitored the hydrolysis mixture, or we monitored the hydrolysis, and then we determined the rate of the reaction. Yeah, and I guess lastly, one other general purpose behind our experiment was to study the structure activity relationships in a base promoted ester hydrolysis. Okay, so first, in the first part of the experiment, like I said, we synthesized the hippuric acid using glycine and benzoyl chloride. We did so by swirling the mixture in a beaker. There was also an alkaline catalyst present. Once the alkaline pH was reached and the color turned to be sort of like a clear yellow, sort of whitish yellow, we knew that the reaction was done. In the second part of the experiment, what we did was we esterified hippuric acid using 4-CL phenol and EDC. And so what our substituent was chlorine. And I mean, other groups had different substituents, so we were doing this just sort of to see how the different substituents would affect it. And so what we did was we used the EDC in order to dehydrate that hippuric acid that was then reacted with the alcohol or the 4-CL phenol. And then eventually what we did was we purified this through recrystallization. Later, what we did was we then hydrolyzed 4-CL phenyl hippurate. In doing so, we then determined the UV of both the starting material and of the hydrolysis mixture, which can be seen above here. And then using the optimum wavelength, which can be sort of found by looking at the wavelengths between the starting material and the hydrolysis mixture and seeing what's different. And using that wavelength, then we were able to use Beer's law to calculate molar absorptivity. And then, so what we did was we plotted a log of the rate constant versus the substituent sigma value in order to sort of display the effects that different substituents have on the rate of hydrolysis. And in our case, the substituent was chlorine. Okay, so next we have yield, purification, and characterization. So we actually ended up dropping our product into the ice bath during our recrystallization step. This obviously affected our melting point and NMR, which we will discuss in a second. And we tried to actually dehydrate the product, but this is kind of impossible since there's water in the solution. So it was very difficult to find the right ratio of solvents in that step. In the NMR, we actually were able to get some correct peaks, but we had too many, and this suggested that the product was entirely pure, which was expected. And this is a likely result of us using some residual product from after the rotovap, which is also before the recrystallization step. So the product just wasn't very pure. As such, we couldn't really get a valid melting point or percent yield for the purified 4-CL phenyl hippurate. And so for the kinetic analysis, we just had to use another group's product. And that was coal and jasmine. That was the group we used.
Yeah, so I'm gonna talk a little bit more about how how we weren't able to continue with the purification steps. So normally the two solvent purification works because the first solvent, in this case ethyl acetate, um is able to dissolve the crude product really well. And then the second solvent that you add, and it's still warm, hexades, when it cools down, the product is able to precipitate out, and then you're able to collect a purified product, leaving behind any impurities in the solvent mixture. And it's really important in order to do this to get the right ratio of the two solvents. And normally that's okay because you only have your crude product. But as ours was contaminated with water, in which our crude product is very soluble, we had to try to get rid of the water. And as Eli said, we weren't able to do that. And then after we tried to then get the solvent ratio correct, was more or less impossible. So we didn't end up getting a melting point and got no yield for this part of the experiment. However, as Cole and Jasmine were so kind as to give us some of their product, we were able to do the hydrolysis. So in this step, we directly obtained from the machine the optimal wavelength to do the kinetic experiment at which Eli talked about. And then we found, again, from the machine, the initial slope of our first order kinetics. So then we were using those, we were able to calculate the molar absorptivity and our rate of reaction. So this was then compared to our peers who also used, who synthesized the same, using the same substituent. And we chose to use UV spectrophotometry because it's a really good way to look at these conjugated systems, which absorb UV light really well. So obviously on the left, you can see the 4-chlorophenyl hippurate, and that's got 2 rings and those double bonds, and it's a very conjugated system and is really good at absorbing UV light. Whereas the 2 products are each individually much less conjugated and are not able to absorb the UV light as well. So there would be a clear difference as the reaction progresses to so that we would be able to see and monitor that through the UV spectrophotometry. So compared to our peers who also synthesized 4-chlorophenyl hippurate and then use that to do hydrolysis, we had a pretty normal, or compared to them, molar absorptivity right in the middle of our peers, and similarly with the K2. And that also compared really well to Jasmine and Cole's. So that suggests that we both of our groups did pretty well to find that data. So here we have graphs comparing sigma and log K2. So this is kind of one of the main goals of the experiment, was to see if substituent has an effect on the rate of reaction. So the sigma value corresponds to the substituent. Each of the 6 substituents have their own sigma value, and a larger sigma value indicates that the substituent is an electron withdrawing group, and a smaller one indicates that it's a donating group. So as you can see, there's a slight positive correlation, which as you can see, the slope is approximately between 1.6 and 1.7. The graph on the left has all the values, but a slightly lower R squared value. So the line isn't as good of a fit. Whereas on the right, there's a this just has the mean of all the K2 values for each substituent, and then the log was taken of those. So there's fewer points, a better fit line, but less data overall. So as you can see, there's a slope for this line of about 1.6 to 1.7, and that's the rho value. So this rho value being above 1 means that there's a very strong correlation between the speed of reaction and the kind of substituent used. So this may be due to the properties of electron withdrawing groups taking away electron density from the alpha carbon. So you can see this better on the next slide. So the above is the molecule that we were reacting, and this is a resonance structure of it. So as you can see, there is a partial positive on the alpha carbon at all times due to the resonance structure. And with an electron withdrawing group at that X position, more electron density will be taken away from that carbon, and then it'll be more susceptible to the attack from the OH minus, which then ends up splitting the molecule into two. So overall, our conclusions were that we did not fulfill the objective of synthesizing for chlorophenyl hippurate because we had a mistake and an error. However, we were able to learn from that, which is really good. We also found a positive correlation between sigma and K2, which suggests and confirms the theoretical properties of electron withdrawing groups and electron donating groups. And of course, we learned about H2O contamination and the reason why how a two-solvent purification step works. So finally, we have our literature, and which provided us with some relevant background, but I thought it was a good idea to include at the end because it kind of shows the broader applications of these reactions and contextualizes them. So it's not just something you do in undergrad, it's something that has bigger applications. So first was an article we found through SciFinder, which talks about EDC specifically and how it was used as a cross-linking agent with porcine, which is pig tissue, and human collagen matrices, and that actually produced clear tissue, which could be used in a lot of different ways. But what they've currently done so far is they've used it in cornea transplants, things like that. And so we found another article about how there is other research going on about substituent effect on amino acid saponification, which is the reaction that we did. So it goes to show that that is an important component of what our human body does too. And to that, actually, when a human body dies and it's decaying, bacteria will go in and do the base catalyzed hydrolysis on fat cells in the body. And there's a article about how that happened at a gravesite in Bosnia and Herzegovina. So overall, thank you for watching our video, and yeah.
Thank you.
Stop the recording. There we go.